Hi everyone, welcome to my YouTube channel Code and Canvas. In this video, we will cover consistent hashing. So let us start. On a distributed server, it's important to distribute requests efficiently and evenly across the servers in horizontal scaling. Because you don't want to one server get overwhelmed with all the requests. So consistent hashing is a technique which is used for the same purpose. For example, if you have n number of servers and when client makes request, you usually use a load balancer, right, to distribute the request on all the servers evenly. So consistent hashing is an algorithm that sits at load balancer or CDNs to distribute the load evenly among all the servers. First, let us understand what is the problem with all the other load balancing algorithms that we commonly hear. Round robin algorithm. You must have heard about round robin algorithm. It's a simple algorithm. It's easy to implement and it evenly distributes the load under stable conditions. Let's say we have three servers, server A, B, and C. Then round robin will route the request something like this. Request 1 will go to server A, request 2 will go to server B, request 3 will go to server C, and in loop again. So request 4 will again go to server A and so on. So the problem with this algorithm is it doesn't consider the server load. For example, if a server 1 has too many requests that needs to be handled already, it will still forward the request to server 1 in the same manner. It doesn't care if a server is already overwhelmed with the request or not. Poor performance on server changes. So let's say these are all caching servers which caches user data. For example, let's say a user A makes first request, right, which will go to server 1. So the data of user 1 will get cached on server 1. Next, other users make some requests. For example, user 2 requests go to server 2, user 3 requests go to server 3, and so on. Now let's say user 1 make a request again. There is no guarantee that it will go to server 1 again. It may go to any other server as well. So maybe server 2, server 3, or any server that is present. So the problem here is it will lead to lot of cache miss because user 1 data was already in server 1, right? The first request of user 1 went to server 1, right? So the caching of user 1 is present on server 1. So if there another request that is coming from user 1 goes to any other server, then it will lead to a cache miss. That is the problem which occurs whenever a new server is added or a server gets failed and removed from the group of servers. It leads to lot of cache misses and lot of redistribution of requests or keys. So there is a poor performance when a server changes. It's not ideal for stateful application. The same reason whenever a server is added or deleted from the pool, lot of cache misses will happen. So for stateful servers, it's not an ideal algorithm. It is an ideal algorithm when the servers are stateless. For example, simple REST APIs which do not maintain any state, and you have a load. You have load coming evenly to your website. So if you want to distribute load evenly, and your request processing time is even, then round robin algorithm is a good algorithm for that purpose. But if your servers are stateful and you want some stickiness basically with your sessions, then round robin cannot be used. So I have put an example for the same purpose. For example, let's say suppose we are adding a new server D. Now the request will get distributed in this manner. Request 1 go to server A, request 2 to go to server B, request 3 to server 3, request 4 to server D. So as you can see, when server D was not there, request 4 was going to server A. Now it is going to server D. So a lot of redistribution of request and keys will happen in this algorithm. Uh, so this will result in more cache misses and there will be potential session drops. For example, if your server, let's say, stores the session data, then on the first request, let's say user one, let's say first request of a user goes to server A. then the session data will get stored on server A. But in the next request, it might reach to server B or server C or server D on any other server present, right? There will not be any session present for that particular user, right? So the session will drop for that user. So this is not an ideal algorithm in case of session storage as well. Also, in case of caching, let's say you have so many cache distributed cache servers, right? So let's say a new server got added, right? Then or a server got deleted, right? Then lots of cache misses will happen, right? So you have to reload your cache accordingly. So the whole cache will be built again in a lazy manner, or maybe when the request comes, the data will get updated in the cache based on which server is receiving which request. So this is the problem with round robin algorithm. So to solve the stickiness issue, we can use static hashing. So in static hashing, let's say each request is associated with a key. So we calculate the hash based on the key. So key can be anything, for example, user ID or some random unique ID that can be generated while making a request. You can use any unique ID as a key. So for example, let's say for a request, each key each key we are generating an hash. For keeping the calculation simple, I have just added 10 to the number of keys as part of the hash value. But you will use in real world algorithms, you will use a proper hashing algorithms like SHA-256 or AES encryption, or many other algorithms are there. So let's say these are the keys. Let's say these many requests are coming with these keys, and they have a hash that are stored in this column. So now let's say we have 4 servers in our pool, 0, 1, 2, 3. So to distribute the load between these servers, we will just divide the value of hash by 4, and whatever the remainder will come, we will just redirect the request to that particular server. For example, key 0 has a hash value of 10. So if we take a remainder by 4, which comes 2, then we will distribute this, redirect this request to server 2. Key 1 has a remainder 3, so we will redirect this request to server 3, and so on. So as you can see, all the 4 servers got a request evenly distributed among them. But so whenever a request comes with the same ID, for example, user 1 has some user ID, right? So let's say user 1 makes a request again. Because the user ID for that user is same, the hash will be same, and hence the remainder will be same. So the request will go to the same server for a particular user, right? So you get a sticky session here. That problem is solved with this. But we have got another problem. What happens when we auto scale the servers, or one of the server fails and gets removed from the pool? So let's look into that. So let's say our server 3 is down. So now it's no longer accepting any request. So now according to our hash tables, we now have only 3 servers, right? Even if the hash value remains same, because user ID is not changing. So hash value for those keys will remain same, but the server that will be accepting that request changes. So as you can see, now we are doing a modulo 3. So key 0 is going to server 1, key 1 is going to server 2, key 2 to server 0, and so on. So if you will compare these two distributions, you can see almost all the keys got redistributed. So I have marked keys that got redistributed by red color. So as you can see, out of 8, 5 keys got redistributed. And also you can see not only the keys that belongs to server 3, which is key 1 and key 5, other keys as well got redistributed, which we don't need to, right? Because server 2, server 1 and server 0 are still online. So they can still serve requests. There is no need to redistribute keys which were handled by them, right? But they got also redistributed. So consistent hashing is a technique to solve these problems only. Let's jump into that. So according to the definition of consistent hashing, it's a special kind of hashing technique such that when a hash table is resized, only k by n keys needs to be remapped on an average, where k is the number of keys and n is the number of slots. So for example, let's say we have 8 keys and 4 servers, and let's say one of the server goes down, then only 8 divided by 4, on an average 8 divided by 4, 2 keys will get redistributed only. uh, let's see how it does something like that. So for a consistent hashing, let's say we have a hashing range. For example, let's say we are using a hash function which produces value from 0 to 2 to the power 160 minus 1. So if you will take example of SHA-1, it produces hash values between the same range from 0 to 2 to the power 160 minus 1. Let's assume we create an array with all these indexes. We create an array of this big size, and we calculate the hash of all the servers. So let's say we have n number of servers. We have created an array of this big size. Now we will create a now if we join the ends of this array, for example, if we join x0 to xn, it will form a ring, right? So x0 will belong to, let's say the array starts from here where my cursor is, then x0 will come here, and while going through this ring, xn will come uh, on this left side of the line, right? So it will form a ring. Now what we'll do, based on this, using the same hash for which we have created this array, using the same hash based on the server IP address or maybe some ID that is uniquely associated with the server, we will generate a hash for each server. So for example, we have, let's say, 4 servers, S0, S1, S2 and S3. For each of the server, using their IP address, we will generate a hash, and we will assign them the slot on the array itself, on this circular array itself, or you can say on the ring itself. So whatever the hash comes, we will assign them that slot. For example, let's say we have slots from 0 to this value, right? Let's say server 0, the value of hash for server 0 comes, for example, 100. Then the index 100 on this particular array or ring will be marked as a server 0. Similarly, let's say server 1 get the value hash value as 1000. Then the index 1000 will be marked as for server 1 in this particular ring, and so on. After mapping all the servers on the ring, let's say whatever keys we will get, whenever the keys will come, we will use again the same hash function we use for creating the ring as well as for mapping the servers on the ring. We will use the same hash function to generate hash for them and map them as well on the ring. So for example, let's say key 0 came, let's say it got the hash 50, then we map it to the index 50, which is before server 0, which is mapped to index 100, right? Let's assume it's mapped to index 100, it's before that. Similarly, for other keys as well, we will generate the hash and map them on the hash ring. Now, to distribute the keys among different servers, we will move clockwise. So for key 0, we will move in clockwise direction. The first server we get in the clockwise direction for key 0 is S0. So key 0 will be handled by S0. Similarly, when we move from K1 in clockwise direction, the first server we get is S1. So S1 will handle the key 1. Similarly for the other keys as well. Now how it solves our problem of redistribution of keys. So let's say we are adding a server or removing a server. Then let's take both the cases. So on the left side, we are adding one more server, which is S4. Let's say it got mapped between K0 and S0. Now as we map the keys with the servers by moving in clockwise direction, right? So only the keys that belongs to the area between S3 and S4 will get remapped, right? Because whatever keys that are present in S4, between S4 and S0, they will still be handled by S0, right? Because we distribute the keys by moving in clockwise direction. So if any key is present between S4 and S0, it was already handled by S0, and after adding the new server, it will again handle by S0 itself. Similarly for the other keys as well. For example, K1 was being handled by S1. Still, if you move in clockwise direction, K1 will still be handled by S1. Only the key K0, which is present between S3 and S4, will get remapped, because now if we move in clockwise direction from K0, we can see the server 4 is the server that is coming first, so it will get remapped. Similarly, let's say if we remove a server, let's say we are removing the S1, which is present, which is there in this diagram on the right side. So now as you can see, S1 got removed, right? Now all the keys that are present that are not present between S1 and S0, which is K0, K3 and K2, they don't need to be remapped, right? They will still be handled by the same servers, because there is no effect on these keys, right? Only the keys that will get remapped will be between S1 and S0, because now there is no server 1 to handle these keys, right? So they will get remapped to the next server present in the clockwise direction, which is S2, and same will happen, same is getting displayed in this diagram. So as you can see, now K1 is remapped to S2. So if we consider the load is evenly distributed between the servers on a hash ring, you can say only the keys that were handled by the server which got filled will get redistributed, right? So for example, let's say there are 8 keys, there are 4 servers, each server is handling, let's say, 2 keys, and if a server fails, then only the key handled by the server that failed will get remapped. All the other keys will be unaffected, right? So it is solving our problem of redistributing of so many keys. Similarly, while adding a server, if the load is evenly distributed, right, only the keys that are present by server 0, that are handled by server 0, some of the keys that are handled by server 0 will get remapped, other keys will have no effect, right? So it is reducing the number of keys that needs to be redistributed while adding a server or a failure of a server. But this type of basic consistent hashing has two problems actually. So the problem is, no matter what hash function you choose, it is impossible to keep the same size of partition between the rings, considering a server can be added or removed. For example, let's say server 4 got added here. Now all the keys that will be mapped to server 0 will be will be uh, will be the keys which are present between this portion, right, between S4 and S0, which is very small. And here, when the server 1 got removed, almost half the circle is represented by S2. So all the keys that will be mapping to this area between S0 and S2, they will go to server 2. So there can be non-uniform key distribution in hash rings. To solve this problem, we are using virtual nodes. Now, what is virtual node? So instead of representing a server by a single node on a hash ring, we create some virtual nodes for each server. Let's take an example. Let's say for each server we are creating 3 virtual nodes. So let's say we have 2 servers. So and each server has 3 virtual nodes. So we get total 6. Now I have randomly put some virtual nodes on this ring. So as you can see, S0, S01, S02 and S03. These are so server 0 is present and 3 virtual nodes are also present here for the same server. Similarly, server 1 is present here and 3 virtual nodes that represents S1 are also present here, S11, S12 and S13. Because they will have each virtual node has a unique identifier, they will get mapped at different positions on the ring based on what hash value they produce. Now the key distribution will be something like this. We will map the keys again using the same hash function on the ring, and we will move in clockwise direction. For example, for K0, let's say we are moving in clockwise direction, and the first server node that we get is S1 virtual node, server 1 third virtual node, right? So this request will get redirected to server 1 because we get the info of server 1 from this virtual node. Similarly, now K5, when we move in clockwise direction, we get a virtual node that represents server 0. So it will be redirected to server 0 and so on. Let's take one more example. For example, it's K3. While moving in clockwise direction, we get a virtual node that is representing server 1. So it will be redirected to server 1. So as you can see, the more virtual nodes you have for servers and the more number of servers are present, more uniform distribution will have. So I have taken a value 3 here randomly just to explain this example. In real world scenario, the number of virtual nodes can go up to hundred, thousands, and more than thousands actually. The pros for this consistent hashing is minimum redistribution of keys when a server is added or removed. Supports scalability in distributed system. So for when you have distributed system, if a server gets added or removed, uh, very less number of requests gets removed, right? So it supports scalability there. It is great for distributed caches like Redis and Memcache because it will reduce the number of cache misses. As number of keys that are going to new servers are less, number of cache misses will also get reduced by a huge amount. Uh, Also, it can handle uneven server loads with techniques like virtual nodes. The con here is it's more complex to implement actually because implementing a simple hashing and algorithms like round robin is much easier, but implementing consistent hashing is a bit complex than that. Also, some performance tuning might require here because having different number of virtual nodes can give you different performance. So a tuning is required on the how many virtual nodes you want to use for your servers. Now, a common question occur here: how do we know if a server is up or down? So, in practice, there are actually two mechanisms that we use to find out if a server is up and down. One is heartbeat, where a load balancer coordinates periodically and sends a signal or HTTP request to each server. For example, let's say every 5 seconds, a load balancer is sending requests to all of these servers that are present in our ring. And if he doesn't get response for n retries, for example, let's say we have configured 3 retries in case of failure in a load balancer, and for all the 3 retries, if we doesn't get a response from a particular server, then we consider that a server down and we remove it from our from our hash ring. Once the server comes back, the load balancer comes to know about it, and we again add it to the hash ring and we redistribute the keys again. Uh, another uh, another way is passive health checks. So instead of making a ping periodically to the servers, we check for the failures. So if the actual request that are going to a particular server fails, for example, let's say the percentage of request failure has increased by 90% in last 30 seconds, let's say, we assume there is some problem with the server and that is down. So we take the server out from our hash ring and we redistribute the keys. Once the server becomes healthy, we add it again to our hash ring. uh, Adding a new server, let's say if you want to, on auto scaling, a new server can be added based on the load, based on the traffic you are receiving, right? So to register a server on a hash ring, you can either use a API or there is something called service discovery, which is used for this purpose. Service discovery use gossip protocols as well, and it is used in many tools like console and etcd, which is used in Kubernetes, Eureka, which is used by Netflix, uh, to register the new servers on hash rings and update the servers which are healthy at a particular interval of time. I will create a separate video on this on servers discovery and as well as gossip protocol because it's a lengthy topic. As this video is already getting long, We will cover the implementation part of consistent hashing in a separate video. I will do a demo on consistent hashing and a code walkthrough in Node.js there. Please like, share and subscribe my channel and leave your feedback in comments. Thank you.